So, hello and welcome to the class. We'll wait for a few minutes for the other people to join. If nobody joins, we'll continue the class, solve some problems. We'll wait for like 3 to 4 minutes. Okay, we'll start the class now. So, yeah. So, this week also, there were ideas on path integrals which was discussed. Path integral was formally discussed. Something quantum mechanics using Lagrangians and all those ideas were discussed and path integral finally came into the way. And so we'll discuss problems on path integrals. We had also discussed problems on path integrals last week, but uh, some except the free particle for the harmonic oscillator, uh, I did not complete everything. Anyways, we will start with the question. So, so we have been given that the free particle Green's function or the free particle kernel that we calculated last time is given as um, this is at some time and position xb, and this say the time and position of this one is x, this is x minus, this is x initial. which we have taken time and position to be 0. So this can be written as n by 2 pi I power half exponential I n x squared by 2h cross 3. Now the first question, show satisfies the free particle Schrodinger equation, which is h cross del derivative t0 is equal to minus 2n. Let's solve this problem. Mm, So let's take LHS and just do the differential d dt t0. So let me put the constant here and then we put is important for us. This is so let's bring this out. I'll put one t from here, and the other t is just t to the power 1, which will give t to the power minus 3 by 2, which is again 1 by t root t. Let us write this properly. Going to give, I'm going to put this t here. So, t. So this is LHS. Now we'll look into RHS. First, we do the single derivative. That is del x of now we differentiate again. I'll differentiate only this part. So that is del x of now we'll combine. So put b in it. And this will give you then your del square q by del square is this. Therefore, minus h squared by 2m is equal to minus h squared minus when we go to 15 minus h square and h square gets cancelled, so minus I h cut n and n gets cancelled, t I'm writing here. And comparing with the LHS, we're having an extra factor of the value, then function of the this two is here. M and n gets cancelled, h square gets cancelled with h, m and n gets cancelled, t I have written it here, and I is here, which is equal to LHS equal to minus h derivative of t. So we have to the free particle formula satisfied Schrödinger's equation. Now the question which comes about is it true for any kernel? Will the harmonic oscillator kernel satisfy the harmonic oscillator Schrödinger equation? Yes, that is the question. Oh, okay. It just takes 2 minutes, and then I just look up the second problem, and we'll start with the second problem. Now we just prove it before going to the last time how I proved this, that it should be some n times classical e to the power I times of classical action. We'll just show what is the motivation behind it. So why are we doing this? What is the motivation behind it? And that is better said in a question. Even a general quadratic Lagrangian of form L is equal to VT Q dot square plus. So this Lagrangian is a function of Q dot as it is. Q dot, but also a explicit function of time. And we have AT Q dot square plus BT Q dot plus CT Q dot DT Q square plus ET Q plus F of T. So you can see that it's a very general Lagrangian. There's Q dot square, Q dot, Q dot is also there, Q square is there. Q square is there. There is this Q square is there, Q is there, F of T is also there. So this is a general function. This is a constant function in Q and Q dot. So if you have this Lagrangian of this kind, then first thing to do is find the equation of motion. Okay. The question is no. Question is given a general quadratic Lagrangian and fluctuations given a general quadratic Lagrangian whose solution is Q classical, and the fluctuations are those, say these are the quantum corrections. Fluctuations about the classical solution is given by eta. Okay. Right. Find the kernel of this system. So let us go to the solution. Our Lagrangian is as given. I'll just copy this. The first thing to find is QC. The first thing to see is what is the Euler-Lagrange equation. That is QC. So just an aside. This is CTQ dot plus 2BT Q plus ET. And the Q dot is AT Now, in the Lagrangian, these are functions of time also, because these are trajectories when you are writing the Euler-Lagrange equation. They also will have a clear t. So I'll drop the t's just for notational convenience. But this means that t is also there. 2 a dot q dot plus 2 a q dot plus b dot plus c dot q plus cq dot is equal to cq dot plus p dq plus e. So cq dot cancels. cq dot cancels, and we are left with 2 a dot q dot plus 2 a dot plus b dot plus c dot q equals p b q plus e, and q classical solves one, where one is this. This has been given to us. Okay, so what this means is, given our space of trajectories, q of t and t, suppose we have a trajectory like this, say it's at point A, this is the initial point A, final point B, and this is the classical trajectory. So fluctuation would mean that there is fluctuation would mean that you are just varying this trajectory somehow. Is it probably going like above the classical trajectory you had, or below the classical trajectory you had, or any trajectory? But we'll assume that the fluctuation is small. Yeah, so that we can take first order approximation. Okay. So these are characterized by, so the condition, these are characterized by the fluctuation. So the conditions on eta is that it should keep the boundary points intact. What I mean by this is eta at A is equal to eta at B is equal to 0. Okay. Now our solution. Now in the path integral, so our q is q classical plus eta. There is a function of t. There is also a function of t. There is also a function of t, and dropping t for notational convenience. Now in the action, well, before going to the action, let's now in the Lagrangian. So now in the Lagrangian, we just put this q and see what we get. So it's a q classical plus eta dot square. So dot square plus b q dot plus dot plus eta plus C Q plus theta Q dot plus eta dot is dq square dq plus dq square is Q plus eta square plus ETQ, which is E possible plus T classical plus eta plus F. Now we'll expand this and keep things up to first order. T classical dot eta dot. Up to first order, this is what it is. Now we will collect the classical terms, okay, which has no eta multiplied to it. That is this term, this term, this term. This has eta multiplied to it, so we're not taking this. So this term, and this term. This is nothing but the original, like the classical Lagrangian for only the classical solution. Okay. And we'll denote these all the summation, the whole of this term is LQs, like LCL. What I mean is, we write everything to be well classical plus the other terms. The other terms being now now what you're going to do is you're going to write this term, write one of the terms as a full solution. I think I missed it. One second. Okay, seems I've made a mistake. So this is the fluctuation. Yeah, actually, the fluctuation will not be small. I'm so sorry about it. So this will have terms, the square terms too. That was the main point of this. So I'll put those square terms also. The first thing, it is nothing but is beta dot square plus beta dot square plus um, this one. So I'll add one more c beta dot, which is the last term, beta dot c, and other terms are just visited. Here too, we are going to add one beta square, and then we are done. Only three terms we will add. Hmm. Plus a beta dot square c beta dot plus beta dot plus beta square. Okay. Now we will try to write all these terms as a full addition. Mm. Mm. You will try to write this term to, as a total derivative. Oh, sorry. So leaving these terms, which is a beta dot square plus c beta dot plus d beta square plus the other terms, which will club together as eta times c q dot classical plus p b q c l plus e plus eta dot p a q c l dot plus c q c l plus b. Mm. Notice this is nothing but the equation of motion. Here it is. Well, the way to see it is, let us take this part, and we are going to have 2AQCl plus CQCl plus B, which is 2A plus 2DQE plus C. Yeah, 2DQE plus C Q dot. CQ dot plus 2DQ plus C. So CQ dot 2D plus C. We are going to write that as, that is dou L by dou Q of dou L by dou Q, and we get this, right? Mm. And what is this part? And this part is 2aq dot cl plus cqcl plus b. So 2aqcl plus cqcl plus b. That is dual by del Q. What I mean to say is we have this. This is dual by dou q plus eta dot. This is dual by dou q dot. Okay. So what we will try to do is we will try to make this same. And to do that, write the above as follows. We want to change this eta and write it as a total derivative. Okay. So what I will do is d dt eta dot aqcl dot plus cqcl is b minus this is eta. So this will differentiate here and differentiate here. I'll subtract the term which differentiates here. That is eta d dt and this is the term which was already there. I'm writing it here again. Keep this term as it is. And as I told you, so I'll put eta together. If I put eta together, this term is nothing but dual by classical I'm going to put minus this term is d dt of dual by dou q dot density. Okay. This I have written it before. So this is nothing but this equation is satisfied. This part, suppose I'm calling it E and I'm calling it B. A and B, that is by equations of motion. And so A plus B is equal to 0. Therefore, our Lagrangian will become L classical plus A eta dot square plus C eta dot B eta square plus B beta eta C A Q dot classical plus C Q C L plus B. Now we are going to put this in the action. In the action, we have integral L dt from some suitable time, say A to B, where A to B it means this is Ti, this is Tx. I'm just going to use A to B as the notation, okay? So I'm going to have the classical Q plus integral will be Q from A LH square plus C eta dot plus D eta square D dt dt then Q A Q plus operator plus C Q plus operator plus B. Now this will just give you limits, and the limits will have this will just give you limits from this part and doing it for this part, calling it C. C will have limits because this is a total derivative term here. So eta of B into A to C and dot plus B, this evaluated at B minus A to A to plus C plus C to C plus B at A. Now eta of A and eta of B is 0, so the whole term is 0. Therefore, we'll have our action to be this. Therefore, the path integral from the finishing point to the initial point or dA, whatever you want to write, is nothing but integral or functional integral over the cubes to the power I by x cut times this. Where Q can be written as Q classical plus Q. So what is this dq? This dq is nothing but like dqi. And you're going to take the limit and then to infinity. Right. This is how you define this. And you are also going to have some normalization factor, which is f, which is a function of anything. Okay. This is how the measure is defined. And you have e to the power I s step. Now, what you're doing is you're going to a new, so you had these qi, this qi were q classical. You are going from q classical to q classical I to qi. Okay, which is equal to q classical I plus theta. So you need to uh, find the Jacobian of the transformation, and in this case the Jacobian is 1. Okay? That means eta I what I mean to say, eta is only a function of time. It's not a function of these q's. That is why you will have qi, which is the new coordinate, by old coordinate. I'm so sorry. Is equal to 1. This is 0. So the Jacobian of transformation is just 1. So wait a second. Yeah. Let us continue. So the Jacobian of transformation is just one, and and these are known fields. They come by solving the equation. So it is only over this. So we are going to have d eta power I by h. S will have S will have this part, which I'll call as S classical, and the other part. Okay. So S classical times e to the power I power I by h cross integral a to b square plus c eta dot sk. With the boundary conditions that eta I is equal to 0, eta b is equal to 0. Now this is just a number. It does not depend on eta, and it has q classical, and you integrate over those q classical from a to b. So this is just some factor, and this factor just pulls away, which is to the power h cut s classical, which has been evaluated, and then you have spark, which is the eta to the power h cut b eta square eta dot is. So this is the reason why you can write the kernel to be some classical action evaluated from your required time times some normalization constant, which will be given by this. Now, one more easy thing, like one more great thing about what we have just shown is that it helps us later in our calculations is that to calculate this normalization, we can just use path integrals again. Like what I mean to say is like, for example, if C is zero, if C is zero and A and D are just one or half, whatever you want to take, then this is nothing but this is in itself the uh, harmonic oscillator kernel, right? This is in itself the harmonic oscillator kernel. Now you find the harmonic oscillator kernel with the appropriate boundary conditions and you will get this part. So deriving this is a very important result. This is a very important result. So I'll put it in a box. It does just take 2 minutes. I'll just uh, find the another problem. G Nothing. So this is the question. Given the kernel of the free particle, which is just okay. So yeah. So what happens? Mm, what happens to this kernel as t tends to zero? That means as t tends to zero, if x also tends to zero, what will happen? What is the, in other words, what is the probability distribution? It says, uh, well, okay. So this kernel is some kind of a probability distribution. It says at what is the probability of a particle. It starts from the initial position to reach that point x and t. Tells you some kind of it has a meaning of a probability associated with it. Mm, and I'm now saying that what happens to this distribution when, you know, what happens to this distribution, or like what is the probability distribution associated when I want the particle to uh, reach from, like, to go from initial condition to the initial condition, to the initial point to the initial point. Yeah, that's the way to say it. Hmm. So this should be one, right? If your particle is at t equal to zero and x equal to zero at t equal to zero, and it has some probability of going x and t, which is given by a distribution. Okay, for x here and t here, x here and t here, it's all different. X here and t here, it is different. So for what is the probability distribution to be here itself? It should be intuitively, should be if it is already here, then the intuition is like, at the same instant it should be here is, it should be one, right? But since it's a probability distribution, we write this properly as delta of t equal delta of t. Okay. But we want to find this result uh, using this expression of kernel. So what we do is we take the limit tending to zero. Now I claimed that it should be 1, or like since it is a probability distribution, it should be Dirac of t, Dirac delta of t. So this expression is Dirac delta of t. But how do I know that it is Dirac delta of t? We'll have to show the integral, the property which is Dirac delta of t dt would be 1. We're just going to show that here. So that is, we put it inside the integral limits, limit t tending to 0 of this expression. So verify, we are doing some verification, right? We check. And we assume that the limit exists. And so I can take it out of the integral. Mm, this should be it. So to perform this integral and to use the result, there's a catch here. There are two catches here which I'm going to discuss. So the catch here, the second catch actually. So I need a minus sign here to perform this integral, right? Because I can just analytically continue whereby a to some complex number and write this as pi by a. Like a pi. So I need to analytically continue, but I need this minus sign. So I need to introduce this minus sign there. Second catch. Second catch. Multiply minus t half exponential minus and the minus I. This says nothing but pi by a. H cross t minus I and over half. It cancels, and cancels. You get 1 by minus of minus, and this is nothing but okay. The first catch is why is the integral over dx? Well, because I didn't phrase out my question properly, it seems. So my question should have been more precise. So you want this, what I've done is I've actually taken the kernel and not put t tending to zero, right? Taken the kernel and I have uh, taken the limit out. I have actually done this. Here, whatever I'm doing this integral of kernel dx. Okay. So if I wanted to check what happens to k as t tends to zero, I should have, I should have written kernel as a function of time. Okay. And so to write kernel as a function of time, I integrate over all x and get a kernel which is a function of time. This is a, this is a function of time. And I see what happens to the limit here. Well, that is what this question means. What happens to k as t tends to zero? But this is how you should do it. Okay, let's do an integral, which will be very helpful for us later. Um, yeah, actually, this is an integral in which is used in all the as a harmonic oscillator and all those things as well. Yeah, and then we will see if we want to do the kernel of this thing or not. Let me just check 2 minutes. Okay, the integral is this. Perform minus infinity to infinity dq exponential of alpha u final minus q whole square plus beta q minus q initial square. So we're going to just collect the squares. Alpha plus beta q square. This term is going to come minus 2 alpha 2 alpha qf q. So what I'm going to do is 2q alpha qf plus beta qi plus alpha qx square plus beta qi square. Hmm, we should take this out. So we're going to have minus alpha plus beta not a minus sign, but I wanted a minus sign. Alright, I'll introduce a minus sign. Minus of alpha plus beta q square minus 2q alpha qf plus beta qi. Well, this is something which is used to find the free particle kernel. And last time I just stated the result. So that is why I'm doing it again. So this I'm going to write as q minus alpha qf plus beta qi alpha plus beta whole square plus minus alpha qf plus beta qi alpha plus beta whole square plus alpha qf square plus beta qi square and alpha plus beta. Okay. So these are just constants. We're going to take them out. So exponential of we have exponential of this part with this multiplied is just positive alpha plus beta. Ah, so alpha plus beta is multiplied. And so you have only this term. And you have this term. Yeah, all right. And this is the part, this is part one. And the other part will be this, which is just integral is square root pi over a, and your a is this. And this minus a little bit again. 65 then correctly. Okay, this simplifies things. There should be, if alpha and beta were had an I in it, then we get a minus I. Okay, that's not good. So minus alpha minus beta, if we had something like that, then we would not I've worried about this minus. Okay. So alpha square qx square is beta square qy square plus alpha beta qy square plus qx. Ah, minus alpha square qx square that gets cancelled plus beta square qy square that gets cancelled, and we have its own minus 2 alpha beta qy here from this part, and in total we have this by alpha plus beta. And so this becomes exponential of alpha beta. You take common alpha beta by alpha plus beta qi minus qf whole square. This is the result. Next question, we are going to go into harmonic oscillators. And we are going to do what we have done last class, but we are going to do it more in an organized manner. Yeah. The calculation of the path integral, even for the harmonic oscillator, is it's it's easy, but one needs to do a lot of algebra. So I'm seeing if there's something else which can be done, but I think I should make it this. This is a the basis should be clear. So yeah. So the first question is, so for a harmonic oscillator, which has this Lagrangian, half mv square, x square minus half m square omega square x square, uh, with three of with x of a is equal to x t, b is equal to x t, and then t b. So classical solution lead to the action Hmm. Yeah. So we have the Lagrangian of this. The classical, the equation of motion happens to be x of t is x double dot t is equal to minus omega square of t with the boundary condition that t q of t the boundary condition was written. The solution is solutions cos omega t plus b sin omega t. This is the most general solution, right? And let's say is a cos omega t a plus b sin omega t b. B is a cos omega t b plus b sin omega t b. This is the solution. Now we'll just put it in the Lagrangian and then we'll. Well, there is one more thing, okay, which we can do, which is kind of which will make our computations easier. Hmm. Which is this dt. So action for us. That's so x of a is this. I need to put it here. X of a minus b sin t. Alpha sin t. This is real. This is real. And x of b is this. I know a now, which is this. From here I'll find from the second equation I'll find b. Uh, so let me find b from here. Xb minus x7 cos omega ta cos omega td. I just put this down here is equal to b sin omega tb minus tan omega ta cos omega tb. Therefore, b is equal to xb cos omega ta minus xa cos omega tb by sin omega tb and sin omega ta cos omega tb and the cos omega ta and the cos omega ta which I just put here cancels with the one which comes from here. This is xb cos omega t minus x cos omega tb sin of omega tb minus tb. Okay, great. This will be and is therefore x of t is xa minus b sin omega t minus tan omega ta cos omega t plus xa by cos omega t, that is x b cos omega t minus xa cos omega tb by sin omega tb minus ta is b times sin omega t minus tan omega ta cos omega t plus x by cos omega t. Okay, cos omega t. That fine. This is way more algebra than what I was thinking. But wait a second. The source. Okay. Now let's look at the trick, which is S, right? Mm, sorry, which is half n square square minus half n omega square x square, and I'm going to do some things here. I'm going to use x double dot and x double dot equal to minus omega square x. Okay, I'm going to use this equation directly here, which is x square is equal to half n x double dot, so half n x double dot, oh sorry, what is the equation? Yeah, omega square x, yeah, minus omega square x. X double dot is equal to minus omega square x. Now x I am going to substitute it here. And I'll have this by minus omega square. Minus minus becomes this, and the other part is just, I have used the equation of motion. So half m. Now I want to get rid of this integral. Uh, that is a bit difficult to do. Uh, for the sake of, uh, well, no, I won't be able to use this. Okay, I'm sorry. So I need to go through the hard way itself. It's not difficult. It's a lot of algebra. So let us go about it. X dot of t is, I'm going to copy the whole thing, and this is easy because we're going to have a omega, and only these functions are going to change. So this becomes cos, this becomes minus sign, and this becomes minus. That's it, done. So the hard part is in, now x dot square, omega square x square. So x dot square. Hmm. So I'm still going to use this thing only. I know what A and B are now, right? So I'm going to use this. X dot of t, omega minus this and omega t, where we have found in the before. The reason for doing that is now I will directly calculate this and then substitute for A and B. That is a reasonable thing to do. In this case, it comes out to be E dot square is omega square minus A sine omega t. X is cos omega t d omega t square omega square A square sine square A square sine square minus cos square omega t plus B square cos square omega t minus sin square. In the cross term, which is 2ab sine omega cos omega, that cancels. And we will rest the remaining of this. So this is A square, this is minus cos 2 omega t. This is B, so B square minus A square cos 2 omega t. Okay. Now we'll find the action, which is integral of half m x dot square minus omega square x from T a to Tb. The integral will be omega square b square minus a square half m integral cos 2 omega t will be sine 2 omega tb and we can probably apply the formula sine of a minus sine of b, which is 2 sine a minus b by 2 and cos a plus b by 2 means 2a. Now b square minus a square is equal to b square minus x minus b sine omega t cos omega t. B square cos square omega t minus x square minus b square sin square omega t a to x b sin omega t a cos square omega t a, b square cos 2 omega t a plus 2x ab omega t a minus x square cos square omega t a. Now b sine omega t a. Let's look at b. B has sine omega t b minus t a. B square will just be this. So we'll copy this and multiply and see what happens. Hmm. Yeah, so this seems to be wrong. Okay. So let us look term by term. B square cos 2 omega t is equal to xb cos omega t minus xa cos omega tb whole square this will get as this, and xb cos square omega t is in this term. Right, I wanted this xa cos square omega ta plus I'm going to have a xa cos omega ta. That's going to make sin omega 2t. Okay, anyways, b is 2xa omega ab. What is it? If is this thing. Xa xb sin 2 omega t minus 2xa square sin omega ta cos omega tb sin omega ta minus 2. Therefore, what we are going to have is 2xb. Okay, this is so better not do this. It's not the right way to do it. We should see some other structure. So I will just do this b minus a is b plus a. Okay. And b is this. Okay, and b minus a is b minus a. I write it to be like you can xa minus b sin omega ta xa cos sec a minus b b 1 minus tan ta 1 plus tan ta minus xa sec ta b1 minus tan ta plus xa sec ta. So we're going to get b square 1 minus tan square, which is x square. A square minus b square. What did I do? Simplify it so much. So I wrote this as xa by sec omega ta b tan omega ta. So that makes it say sec ta minus b tan ta. Xa sec ta minus b tan ta. And I corrected b together. B minus minus plus 1 plus tan ta minus xa sec ta. B b minus 1 minus tan ta plus xa sec ta. And now this is, oh, okay. A minus b is some other thing is equal to this. This is my friend. B square sec square theta minus x square x square theta. These two terms are going to come, and 1 minus tan square sin by cos, oh, 1 plus tan square is this. Ah, this is my fault. Okay, maybe we have to put b in this now. In 1 plus tan t be written in some other way. 1 plus tan t equal to 1 plus sin by cos is cos plus sin by cos. Tan t plus pi by 4 is equal to plus tan t minus tan t. Okay, anyways, this will actually simplify. Actually, I've made a very big mistake, to be honest. If I had just chosen such that, this tan ta is 0 to simplify, okay, take ta to be 0. Then this is going to simplify a lot. This is going to be just ta is 0, sec a is just sec of 0 is just 1, b plus x is going to simplify a lot. B square minus x square. Alright. And b is xb minus xa cos omega tb divided by sin omega big T. I'm going to write this big T minus x square. And this is also so this whole square. And you're going to get xb minus xb square minus 2xa xb cos omega tb plus x square cos square omega tb minus x square sin square omega tb by sin square omega tb xb square minus 2x into xb cos omega tb plus x square cos 2 omega tb plus sin square omega tb. Now you just put it here. This evaluated as this. This is going to be omega square t we put it to 0 sin omega tb cos omega tb b square minus a square is xb square minus 2x xb cos omega tb plus x square plus 2 omega tb by sin omega tb square. So this cancels with this. We are going to get omega square plus omega tb equals cos by sin is cot omega tb xb square minus 2x xd that should be really you're making some mistake. I'm happy. I'm just going to write this. Let's try to see what is better than will declare a manipulation m square omega square cos. I'm going to put it inside sin omega tb xb square cos omega tb plus xa square. I'm going to open this again cos square omega t minus sin square omega t minus 2xa xb cos square omega tb omega square sin omega tb xb square. Okay, this is a wrong answer. We did not require that. Anyways, it comes out to be this. The next class I'll continue this problem in the next class. I'll continue it from here. Mm. Alright. Plus, we are going to find kernel of. I'm going to guess anything. This we are going to this, and then we are going to see how Gaussian wave function evolves in time, and then we're going to do using the results which we had found in one of the questions. Uh, we're going to do some derivation. Okay, I'll end my class here. Thank you. Mm.